Under Files, there'll be a folder that says Online Lectures, and there's 2 sets of notes under there now. One says Snow Day Lecture Notes, and the other says Snow Day March 3rd Lecture Notes, because we've had 2 snow days, right? On those notes is the URL to the online lecture, so you're welcome to go watch it if you want again. And the notes for that online lecture that I used ChemDraw to make the notes as we went along are there as well. So you can do a play-by-play there. Okay, so those notes are actually sort of a review of last week and to sort of remind you that this concept of electron donating groups and electron withdrawing group concept is very, very important. We see it again and again in terms of activating versus deactivating, directing effects, all sorts of other things. Today we're going to jump into the acid-base realm and sort of understand how those groups can affect acid-base properties of these aromatic compounds. But to start, let's start with the synthesis. So I found this blue chalk, which I seem to kind of like. So we're going to work with blue until I'm out of blue. But this is kind of a nice color, and it erases so well. How would you make this compound here from benzene itself? So why don't you take a couple minutes and see if you can't figure out how to do this. It's always good to try to start, get it wrong, figure out what went wrong, as opposed to just waiting 2 minutes and waiting for me to tell you what the right answer is. I was just talking about this actually with my friend on the way here. My daughter used to take these tests, these pre and post tests in 1st grade, and they told her on the pre-test she could just put a smiley face if she didn't know the answer. So my daughter's pre-tests were all smiley faces, and they used to tell me that she learned so much. I said, that's because you told her she didn't have to do any work. That was it. She loves smiley faces. So let's try for some work. It's better to be wrong than, put some smiley faces down.
So first do that, then add the methyl, yeah, because it'll be meta. You can go back and add this thing to make the is L-carbonyl an ethyl. I think that's how you do it.
All right, one of the first things to note is the meta placement, right, of 2 R groups. And each of these R groups is OP directing. So that's problem number 1, right? So we've got to think about ways that we can get these meta placed. The second thing to note is that there are 2 R groups, and to begin to think about how you can get just an alkyl group onto the ring, right? So there are a few ways that you can do that. You can use Friedel-Crafts alkylation. You can use Friedel-Crafts acylation, followed by some reduction. I know you guys like to use the Clemmensen reduction because that's what's in the second language book. I'm picking that up now. I don't read the book myself, but I've heard enough people talk about it that I know it's in there. So these are 2 possible ways, and the other way is to do some sort of halogenation and then follow this up with some sort of Gilman reagent, right? So these are 3 ways that you know to get an R group onto the ring. So we sort of have to be thinking about that. Now, one nice thing about this is that you can see from this, the use of this, it's going to get me a meta director on the ring, right? None of these others are going to get me a meta director on the ring from the get-go. So one of these R groups has to be added through this methodology, right? That's one way to get it on there. So there's likely other ways to do this, but we'll follow through with, say, one way to do this. So if I take this, I'm now going to be able to come to this on the ring. Again, this is a meta director, and I know that when I reduce this, either using hydrazine as I purported in class or the Clemenson reduction, you can actually get down to an ethyl group, so you have ethyl benzene. So that's a framework to start from. And it also allows me the meta placement of a CH3 group, right? But I know, and this is where some of you are going to begin to lose points, I know that I can't do reaction number 1 right now. There's a couple reasons why I can't do CH3Cl with AlCl3. 2 that I can think of right off the top of my head. What are they? It's an electron withdrawing group. That's the top reason, right? I cannot do alkylation or acylation of a ring that has an electron withdrawing group on it, okay? So what Caitlin did talk to you about in class, and she did direct you to that table, which I think is on page 703, right, is the idea that there are strong activators, moderate activators, weak activators, weak deactivators, moderate deactivators, and strong deactivators. And these 2 were my resonance models. These 2 are my inductive models. These last 2 are also a resonance model, so it's in essence saying that all the weak effects are always an inductive model and not a resonance model, okay? So all of these deactivators, in essence, pull electron density from the ring, okay, either inductively or through resonance, and hence you cannot do any Friedel-Crafts alkylation or acylation of these types of rings, these substituted rings, okay? You should be able to take all of the sort of mono-substituted rings that you can think of, and there's sort of an exercise to do this on the weekly quiz, and place them into one of these categories. These categories are really important to us because they help us with directing effects in terms of what's the most important group to pay attention to in directing effects. It helps us with nomenclature, etc. So there's lots of reasons to sort of be able to place these into this table, okay? So when we move on back to this example, I cannot do now Friedel-Crafts alkylation, that's number 1. There's another reason why we can't use RCl, AlCl3 to get a methyl group on the ring. What was that reason? It's a methyl carbocation, right? And the methyl carbocation isn't very stable and doesn't have a high yield. So we're a no on that. One thing we can do, though, right now is brominate the ring, right? We can do this last step here. We can brominate this ring, and that will give me now a PR that's placed meta with respect to the acyl group that's on there. And I will be able to use my Gilman reagent to swap out, right? So a Gilman reagent is a coupling reaction that will substitute now the Br for the R group that's in parentheses times 2, right? So it's a swap out of the Br for whatever's in these parentheses, and that gets me very close to my final product. The last thing I need to do is reduce, right? So you can either do the Clemenson reduction, or you can use what we've reported in class, and this will get me to my final product. Okay? There are questions about this synthesis here and how we put it together and sort of the limitations. Yeah?
Should that be BR2, FeBr3?
Oh, BR2 can be used, yeah. So AlCl3 and FeBr3 are just Lewis acid catalysts. You can use any Lewis acid catalyst for anything. There's no reason to use FeBr3 with Br2 and FeCl3 with Cl2. I mean, it looks nice and it coordinates kind of like how you match, right? Which my husband says I'm terrible at, but I'm pretty sure the shoes match. He left before me. So I'm not really exactly sure, but I'm pretty sure. My son says they do, but I don't think he matches well either. Yeah?
So can we do zinc and mercury in there instead
Yes, you can use zinc mercury. Yes. Can you just talk a little bit louder?
Sorry. When you do the gilman,
Yep.
do you use ethyl plus pH2, pH6, or over there is the final product ethyl plus?
No. So I've swapped out my meta placements. My methyl's down here, my ethyl's up here when I'm all done. Yeah. But it's the same thing. They're meta placed. Good question though, because diagrammatically it looks different. Yeah.
Does it matter the order of the last two steps?
Does it matter the order of the last two steps? The order of the last two steps does not matter. Okay. All right, great. So you should be looking to be able to do something like this. The homework is coming out, right, tonight? Well, today. Actually, it's done, so I'll put it out as soon as I get back. And it's due Friday, right at the beginning of class. There are some synthesis questions on there. Okay, so make sure that you're understanding these reactions. Come on into the office if you need help. Today we're going to be talking about acid-base chemistry and how electron donating and withdrawing groups play into acid-base chemistry of substituted aromatics. There are three types of aromatic systems that you should be able to order in terms of how substituent affects the acidity or basicity, okay, on an exam. There is a separate question on your homework that's asking you to do it, but it all falls into the same thinking category, okay? But the three that are absolutely fair game for your exam are substituted benzoic acids, substituted phenols, and substituted anilines. These are the ones that we're going to be talking about in class. Your homework takes a little bit of a different take because you have a little bit extra time to think about it and order them and show resonance and all the rest of it. So, but these are the three that you're going to have to be, or you will be held responsible for in the lecture environment. So, let's start with phenols here. So this is phenol, and its base pKa is 10, right? 10 is its base pKa. And we come at 10 by understanding that this alcohol is a special type of alcohol because it's got the aromatic ring attached to it. The aromatic ring allows for more resonance structures to be drawn, therefore stabilization of the conjugate base. One of the biggest things that you need to be able to do, explain, and show is stabilization of the conjugate base, because all acid-base chemistry is built on reciprocity, right? The rules of reciprocity. And reciprocity, in essence, is that a stronger acid leads to a stable, non-reactive, weak conjugate base, right? So a strong acid dissociates to give me a weak, stable, non-reactive conjugate base. So this arrow is symbolizing the reciprocity piece, right? So strong acid, weak base. Weak acid, strong base, right? That's the rule of reciprocity. So when we're considering now how something's going to affect acidity, we need to consider the conjugate base and how stable is the conjugate base in the presence of said substituent at said place on the ring, okay? But it really all comes back to this group here, this little chart here that I sort of sketched out on the right board, okay? Because there's electron donating groups and there's electron withdrawing groups. Remember, this is our sort of line in the sand, right? Between what on the top is electron donating groups and what's on the bottom, electron withdrawing groups. So, I'm going to throw out a substituent, and you're going to tell me where it goes on this chart. Methoxy, which is OCH3. Where does that go? How about I categorize them so we make this a little bit easier? A, B, C, D, E, F. Methoxy. A. Okay. Methoxy does belong in A. What is it about the methoxy group that belongs in A?
Lone pair.
The lone pair on the directly attached atom to the system. My squiggly line here is my system. My system is always going to be these benzenes here, right, in this unit. Okay, how about iodo group, an iodo group? A, B, C, D, F. D. Okay, this is where all the halogens go. Why does it belong in D? What makes these halogens belong in D? They're electron withdrawing by what model, though?
Inductive.
Induction. It's an inductive electron withdrawing group, right? Induction, meaning it's never going to have a resonance example necessarily in terms of how it behaves with the system unless push comes to shove. The only time these halogens step up to the plate for resonance is when there's a positive charge directly on its neighbor, right? Then it capitalizes on the fact that an octet, even though it offers it a weak pi bond because of the length, it's a longer length there, is better than no pi bond and a lack of octet. So that's just a push. It's pushed into that role, but it does not behave that way from the get-go. Okay, how about NO2, a nitro group?
F.
F. So F belongs down here. Remember, a nitro group has a positive charge on the directly attached nitrogen. That's problem number 1. And number 2, it's an atom that's involved in a pi bond to another electronegative atom. Those are sort of telltale signs. Okay? How about an acetate group, which is O, C double bond O, CH3. Acetate, an acetate group.
F.
This is a good game, isn't it? We should have played like The Price is Right, like last week. Last Monday we should have played The Price is Right, right? There should have been a button. I actually have a button in my office that says I don't think so. It would have been totally appropriate in this circumstance. Could have had you place them. Maybe we'll play this on Friday. This is where an acetate belongs, okay? B, all right? An acetate belongs here because, someone tell me, the lone pairs on the directly attached atom, but does it resonate only toward our system, the benzene? No, it resonates in 2 directions, right? It can resonate in this direction toward the benzene, but it can also resonate in the opposite direction toward the carbonyl. Classic moderate activator, okay? All right, how about our carbonyl that we had on the ring over here? Something like a ketone. There's an acyl group on the ring. C double bond O, CH3. No octet in there.
F.
Going to be in D. That's exactly right. So this is where this guy goes, right? D, because its directly attached atom is involved. Did I say D? I meant E. I didn't mean D. I meant E. I do see that it's in E. I said D, though I don't know why. So this is involved in a double bond attached to an electronegative atom. So I have one missing category here. Give me something that'll go in the last category we have. C, what is it? Something like any old R group, right? Any old alkyl group. So styrene even belongs in there, right? That vinyl group belongs in there. I saw that. Yeah, that's vinyl. So vinyl groups belong in there as well as any alkyl group. Methyl, ethyl, isopropyl, etc. Okay? You need to be able to place these in here. I can see that we can't play the game very well, so this is absolutely on your test. I will play the game. So be ready to play the game. Are there questions? Yeah. E. This ketone group there is off of E. So we have an example of everything. I'll run down from the top just to be careful. Okay? The top strong activators. We have anisole at the top, right? OCH3. Other things that belong. Can someone give me another example of a name of a monosubstituted benzene that belongs in that category? Nope, not toluene. Phenol is a good answer. Good. All right. Moderate activators. Moderate activators. I don't know if you know any of the names of things that belong in that category, but another example would be to swap out maybe the oxygen for a nitrogen. That would be another example of a moderate activator. A weak activator, toluene belongs in there. Weak deactivators are all these halogens attached. Moderate deactivators are any acyl groups attached, whether it's attached. The basic thing, actually, this is actually a good sort of concept. See how this group, the acetate, is attached through the oxygen? If the acetate is actually attached through something different, like the carbonyl, this actually switches categories quite different, huh? So you see that? That's actually a play on this sort of thing, so be careful with that sort of thing. As well, we said the strong deactivators are things that are going to be strong resonance models. Okay? Are there any issues with this categorization over here? Yeah.
What would you say with B again? I missed the phenol and anisole was for strong, and then moderate was what?
well, you don't know how to name those, because I was asking for name systems. You don't know how to name them. I can throw out the names, but then you're not going to know what the heck that is, right? So I was saying you can swap out the oxygen for a nitrogen. That would be another example of one. Okay? Yes? An R group is any CH chain, so a hydrocarbon attached. Okay? All right. Now, remember that these have to be directly attached. So if that direct attachment, say, was CH2, CH2, and then a ketone, that has no influence anymore, right? So if the R group is directly attached and somewhere down that chain there's some other functionality, it's ignored because the direct attachment to the ring is actually that R group itself, hydrocarbon in nature. Okay, so our base phenol is 10, and so what we want to start thinking about is where do some of these substituted groups go. So I'm going to put some substitutions on the board, and I am going to give you time to mess this up for a while and talk about it and talk down the wrong path until we can kind of get you back squared away, okay? Because you've got to be able to think through these on your own. If you can't think on your own, then there's going to be a lot of trouble here. So here we go. Here are some phenols that you are going to tell me where they belong with respect to the base phenol. Now I'm going to label them, which doesn't at all match the labeling here on the right board. Not at all. It's just labeled. Maybe we can do Roman numerals. I'm going to go backtrack. We're going to do Roman numerals. All right. I'm going to give you 5 minutes on the clock to order these. Include phenol in your ordering. Okay? I'll make that last one here. And then we will talk through this system. This is literally like a 15-point question on your next exam, okay? And it's like a 10-point question on your homework. So we're talking lots of points here in the short term. So make sure that you can get through the thinking on this, and you can work through the resonance structures and the conceptual arguments that need to be made, okay? 5 minutes on the clock, and then I'm going to go, and I'm going to show you how to think through it, and you're going to retract maybe some of your placements, and we'll work on it, okay? In terms of pKa, so your homework, we're never going to have an issue again, says, you know, most acidic on the left, least acidic on the right, okay? So you have a scale to work from, okay? So most acidic to least acidic, go. I'll walk around. I'll watch you. Kim will be on her feet too. We'll see what you're doing. We'll see if you can draw some resonance structures and talk about it and see it. Start with resonance structure. Start with resonance structure. It's a good idea to draw a base resonance structure and work from there.
Is the nitro group in ortho position the most acidic? Because it's a nitro, it's got a dipole movement, and it's also meta, so it's like all in one direction.
Yeah, the polarity is greater in the ortho.
For the nitro?
Yeah, in the ortho position.
But does that make it more acidic?
Yeah, more.
Yeah.
Yeah.
So the nitro in ortho with the alcohol acidic in this case. Does that make the is the NH2 more acidic than the chlorine
Well, remember the electron pair on the NH2 doesn't contribute to the resonance.
Oh yeah, you're right.
But the NO,
But the
that
NO
one has so much more resonance structures than it.
Wait, the most acidic on the right, right?
Oh, I'm just gonna label mine whatever it is, and then I'll figure out what she said.
So far I said 3 was most acidic.
Wait, it has resonance structures, which increases its acidity depth. Sorry.
Does that make 4 the next most acidic? Yeah.
Oh no, it is.
How am I gonna label this next acidic?
Halogen
The
usually a
low
greater
energy
inductive
chlorine
effect than NH2, right?
It does. Do you see why we said that was the most? Or this one? This one's the most. Did you get yeah. And it's got the nitro.
Did you get 3, 4, 1,
Hold on. 3, 4, 1,
2, 5,
6, yeah.
See, I don't think it's like that. I bet there's like, this is supposed to go
I
there
don't know
because
if
you
it's
forgot
like
this.
NH2 or chlorine though.
No, I think chlorine has a greater inductive.
Really don't want to be condescending. I don't want to sound condescending. I recognize that it sounds a little bit snarky and condescending, but at this point, we should be able to draw resonance structures. So if you can't draw resonance structures, you got to own up. You got to own up and come in and learn, okay? Because I'm here to teach you, but I can't teach you if you don't own up and come in and learn. So no resonance structures drawing on the next exam means lots of points lost. So that's up to you. You choose, all right? So these are the resonance structures, though, that we can draw from phenol. So I'm trying to get you guys all to draw base resonance structures here, okay? So I'm trying to encourage you to draw them of the conjugate base because we really want to consider how to stabilize the conjugate base, okay? So what it actually tells me in phenol itself, right, is where there can be an electron pair and a negative charge. So if I go back to phenol itself, and all the substituted phenols, it does not matter, right? These resonance structures tell me that there's a negative charge possible on each of these ortho positions and off of a para position, okay? So I've taken knowledge that I garnered through resonance, and I am purporting that I'm going to just slap that onto phenol so I can use that as sort of a base strategy, to use that to consider what's going to happen with all of these substitutions that I have. Okay? Does everyone understand what I've done here? It's just a resonance argument. Okay. So this is how I think through the process. Because there's a very, there's always a very defined way that you can think through it. This is the way I think. I realize that it's very, I don't cut any corners, I don't do any of that. But it does work, and it's sort of a decision tree process. And I encourage you to try and come up with these concepts, these methodologies for thinking that don't allow you to cut any corners so you don't miss out on anything. The first thing I do is I slap these into categories. I slap them into electron donating categories and electron withdrawing categories. Number 1, okay? Because if I have an electron withdrawing group on the ring, no matter what, if I have an electron withdrawing group on the ring, okay, it's going to stabilize that negative charge, right? If I have an electron withdrawing group on the ring, it's going to stabilize that negative charge, okay? Bottom line. And if I have an electron donating group off the ring, it's going to destabilize that negative charge, okay? I'm trying to think about the negative charge here. That's what I'm trying to consider when I'm looking at this molecule, okay? Things that stabilize negative charge are deactivators, right? Electron withdrawing groups. They either do it inductively or through resonance. But regardless, they pull electron density toward themselves, thus spreading out electron density and stabilizing the conjugate base. And electron donating groups are things, whether it's inductive or through resonance, that push electron density toward a negative charge that I'm trying to stabilize, right? That's not stabilizing the negative charge. That is for sure destabilizing the negative charge. So as I consider what I'm going to do in terms of ordering them, my base phenol is going to be my turning point, right? I should have things that are directly below it and things that are directly above it. So if I consider this now my more acidic side, which would make sense because that's, if I had a number line, right, 0 would be to the left and 100 would be to the right. And this would be my less acidic side. Phenol is going to sit right here in the middle, right? And I know when phenol sits right in the middle, I know things that are going to be less acidic than phenol are going to be anything that has electron donating groups on the ring. So I have 2 examples of that, right? What are they?
NO2, 3 and 4.
I only have 2 examples of electron donating groups on the ring. What are they? What numbers?
Sorry.
1 and 2.
1 and 2.
Okay? So I'm not suggesting this is the order, 1, 2. I'm just saying I'm ordering them such that this is my electron donating side, and I'm going to expect that they have pKa's now higher than base phenol because it's going to destabilize the conjugate base. And when I destabilize the conjugate base, I'm making the acid weaker. Okay? If I destabilize the conjugate base, I'm making the acid weaker. Okay? All of these other categories are going to fall to the left, right? So they're all going to be more acidic, all of them, 3, 4, 5, and 6. These are all going to be more acidic. These are all examples of electron withdrawing groups, whether it be inductive or through resonance, and these withdrawing groups are going to stabilize the negative charge, right? They're going to stabilize the negative charge, and hence they should be more acidic. The next thing I'm going to do is I'm going to look at each category and I'm going to discern whether or not they are inductive or resonance effects. Okay, so that's number 2. Number 1, I parlayed into donating and withdrawing groups, noting how that's going to affect the pKa. Number 2, I'm going to parlay into inductive effects and resonance effects. Inductive effects are weaker effects. Resonance effects are stronger effects. Okay? So I don't have to worry about that up here because 1 and 2 are both NH2s. I don't have inductive versus resonance. They're both resonance because NH2 falls into the strong activator, so it's a resonance model, right? But I can begin to order 3, 4, 5, 6. 5, 6 are definitely inductive models, whereas 3, 4 are definitely resonance models. So now I'm able to say, okay, 5, 6 are going to be ordered something, like this as a set. I don't know if it's going to be 5, 6 or 6, 5. We're still going to go through that. And then I know 3, 4 is going to be more acidic than that because it's a resonance effect. And resonance is a better way to stabilize the negative charge than an inductive model. Okay? Number 1 was donating versus withdrawing. Number 2 is inductive versus resonance. Number 3 requires that I know something about the difference between an inductive model and a resonance model. This is where we run into a little bit of trouble. People can order down to this, and you'll get points for ordering down to this. Okay? But the fine-tuning is as follows. Okay? I'm going to start with the inductive model because that's the easiest one to start with. Okay? Inductive models fall off with distance. I don't know if you go back to your acid-base chapters. You all love those Klein books. If you go back to the OChem 1 Klein book, there's an acid-base chapter. It talks about that inductive model. And it uses examples of substituted carboxylic acids, I think. It has like this carboxylic acid, and then it has this carboxylic acid. And it says that this one is far more acidic than this one, right? Because the Br is moving further away from where the negative charge is. The inductive model falls off with distance, for sure. Okay? So the closer that halogen is in this case, to the negative charge, the more stabilizing it can be. As it gets further away, that negative charge doesn't sense it at all. There's no sense of it at all, okay? So an inductive model is how close the group is to the the atom that I'm trying to stabilize. Ortho is going to have the biggest effect, right? Ortho is going to have the largest effect. That will be the most acidic because it's the closest. Meta falls off to some extent, right? It will still have an effect. And para is going to be the weakest effect, okay? So when I go to order these, I say, okay, this Cl is meta. It's going to have a bigger effect because it's closer than the para substituted, okay? So I know then that this ordering is actually right. It's 5, 6, and then 7, okay? Because 5 is more acidic because the Cl is meta placed closer to the O minus of the conjugate base, and the Cl, when it's para placed, is the furthest it can be from the O minus, okay? So induction is all about how close I am. Ortho is the biggest effect, meta is the next, and para is the weakest, okay? The resonance effects go back to what I know about my resonance structures, where the negative charge can reside. So I'm going to take that base resonance and I'm going to apply it into my systems. Let's work with 3,4 first. So here's 3,4. I know I can have a negative charge here, here, and here, okay? And on this one, I can have a negative charge here, here, and here, okay? It's the same places, right? Ortho with respect to the OH and para with respect to the OH. That's what I learned over here, right? That the negative charges will always be either ortho or para and never meta, okay? So when I consider this, okay, I know that I'm going to be able to further stabilize any ortho-para resonance withdrawer, okay? I'm going to draw the exact resonance structure that I'm speaking to right here on the board over here, okay? Actually, maybe we'll put it in over here. So when I look at that exact one, this is the one resonance structure that is the savior for all of these. I put in my nitro group here now. Okay? This guy is the savior, because what can happen here? It can continue out onto the chain, creating now a fifth resonance structure that looks like this. Okay? So this is a fifth resonance structure I can draw, and I can draw it when the nitro group is ortho or para, but I can never draw it when the nitro group is meta, because there's never, ever a time where that electron pair is exactly on that meta-placed nitro group, okay? There's never a time where it's exactly on that, okay? So I have 5 resonance structures when my electron withdrawing group is placed ortho or para, and I only have 4 resonance structures when my nitro group is placed meta. Yeah?
Is it kind of like how the OH group is ortho pair directing anyway?
Yeah, it is, because that's where the base resonance structures come from. But the thinking is a little bit different after that, right? Yeah. Because we were stabilizing a positive charge there, right? We're trying to stabilize a negative charge here. Do you see the difference there? Yeah, but it's the same base resonance structures to start from. Yes?
Since that partial negative charge is, or actually the negative charge from resonance is on the para and the ortho, what happens if it were on the para?
If it's on the para, I would also have 5 resonance structures.
So what would you do with the acidity?
Oh, okay. That's a good question. So if it were an orthonitro or a paranitro, okay, so the nitro group actually, all electron withdrawing groups, surprisingly, maybe not, have both inductive and resonance effects. Their resonance effects are a larger effect over their inductive effects. So the O effect is usually greater than the P effect.
So if we had to rank, it would be orthos and para.
Yeah, I don't think that I'm going to ask you to do that, but yeah, yes. Okay, so when I look back over here then, I say which of these is going to be more acidic? Do we think it's 3 or do we think it's 4? 3, okay. All right, now the trouble comes when we have to reverse the trend here, okay? Because these withdrawing groups at ortho-para are glorious, right? But a donating group at ortho-para would be
Inglorious.
the worst, right? A donating group at ortho-para would be the worst. Am I right? Let's look at that. So I have now, my last ones here are 1 and 2. So I'm telling you a donating group, when I'm trying to stabilize a negative charge, a donating group in ortho and para would be the worst. So I'm going to go and modify my diagrams over here to find the para one and show that. Okay, so I'm going to erase the nitro ones and go right to that para one. So hold on just a second here. This is no longer a problem. We don't really care about this one anymore, but we'll draw it. But we do care about this one, okay? This is the one that I care about down here. I'm going to raise it up a little bit. In fact, maybe I'll just draw it up here. Maybe I'll just draw that one. How about that? Here we go. What do we think about this resonance structure right here? There are 4 resonance structures. This is 1 of 4. There are 4 resonance structures. This is 1 of 4. What do we think about this resonance structure right here? Oh, come on. You got to have an opinion. It's bad. It's a bad, bad, bad resonance structure, right? It's horrible. It's a horrible resonance structure. So really, it isn't going to contribute. So what actually happens is we get knocked down by 1. Any ortho and para group that's placed, an electron donating group that's placed ortho-para is going to be terrible in terms of resonance. So when I come out here, my ordering out here then is going to be 1 first and then 2. 2 should be my least acidic because that has a para-placed electron donating group. A para-placed electron donating group. How about that? Okay, we're going to go, you have a question? Yeah. Why is that bad? Because that nitrogen has that first of all, it's electronegative to some extent. But second, that nitrogen has the propensity, right, to donate or push electron density into the ring. And when the negative charge is right there, right, it's in essence making it more negative, less stable. Okay? All right. Let's try different phenols. Here we go. Ready? Okay, which ones are going to go in my more pile? J, K, L, M. J is definitely going to go into more acidic because it's a withdrawing group, right, of the inductive nature. What else? M, because it's a withdrawing group of a resonance nature. Okay, those are the only 2 because the last 2, K and L, belong in my less acidic, right? K and L belong in my less acidic. K is a donating group, resonance model, and L is a donating group inductive model. Okay? All right, so let's work down on the more acidic side. Do I have a separation here between induction and resonance? Is it as simple as that? The answer is yes, it is. So which one is most acidic? J or M? M, great. Because most acidic is going to come from the resonance model. And it will come from a resonance model where there's OP placed groups. Okay? Up on the less acidic side, I'll get you after class. Up on the less acidic side, here I have K and L. Which one of these is going to be more acidic and which one's going to be less acidic?
K.
Okay, is L going to be closer to N or is K going to be closer to N? L. Okay, that's exactly right. Because L is inductively donating, which is less destabilizing than something that's resonance donating. Okay, good luck on your homework. We'll be talking about resonance in the office. Come on by.